We're going to cover section 8.5 now on similitude in chapter 8. And so we're right here in the list of sections. I also want to point out that so we're going to define what a model and a prototype are, and then we're going to explain what similitude means, and in particular what geometric and dynamic similitude are. And define the criteria for achieving similitude. I also want to mention that sections 8.6 through 8.9 are really applications of similitude, and so we likely will just be working problems from those sections in class. So let's go ahead and flip ahead to this particular section and get started. Let's look at the definition of similitude first of all. Similitude is a theory of predicting prototype performance from model observations. So the first thing that we need to do is define what a prototype is. And this is a prototype might be like a new vehicle or a new aircraft, but it's a full scale, something at a full scale. It's a prototype of a new something new that we're building. But it is at full scale. A model, on the other hand, is typically at a smaller scale. So this would be a small scale model of a prototype. So when we talk about similitude, we'll be talking about both the prototype and the model. And so this particular branch of engineering involves the application of pi groups, in particular like the Reynolds number, the Froude numbers, to predict the performance from model tests. Now that's very important because if we can define some sort of connection between the prototype performance or from the model observations to the prototype performance, we can perform experiments at a smaller scale, say in a wind tunnel or in a hydrologic tank, a flume, for instance, and use those to predict what will happen at the full scale when we actually build a production model. So engineers need to make decisions about the design and construction, performance and testing and analysis of models and how they pertain back to the prototype. So can we think of examples where engineers have used models in industry and research? And so some of the things that obviously come to mind are things like aircraft. Certainly Boeing has wind tunnels where they do extensive testing. Also auto companies on automobile testing. Sometimes you see these, you've seen examples of these from the automobile industry, high-speed trains, and so forth. And so these are examples in the transportation industry. In civil engineering, we might have flow and spillways for dam operations or dam design, river models for flood control using flumes, where we just set up a river at a small scale and with a particular channel and look at that. We can also, in those sorts of studies, look at sediment transport. And so this is something that we can do in civil engineering, and also drag on ships. We have shipyards over in Bremerton, Washington, that construct ships, but they have these big areas for doing testing and construction mainly, and maintenance. Also, wind loading. Wind loading on buildings are another example. So if I can squeeze this down here, wind loading on buildings. So buildings present a certain profile to the wind, and so in a wind tunnel you can set up a mock model downtown area with skyscrapers, and then do some wind testing on what the forces are on the skyscrapers, for instance. So similitude depends on a couple of different things, and the first thing that we can easily conceive of is what's called geometric similitude, and this is that we have an exact geometric replica of the prototype. And so this would be the prototype. We would go out and we'd measure the width and the length and perhaps some other dimensions of the prototype, the actual unit. In this case, it looks like a ship, and then we can make a direct connection between the length, the width, and this other dimension c, and these dimensions all have to equal the ratio of these dimensions between the model and the prototype all have to equal a constant value, so that it is truly an exact scaled down replica of the prototype. The dynamic similitude is a little bit more complicated, but it allows some very powerful techniques that we can use in prototype testing, model and prototype testing. So this is very key to understand that dynamic similitude is not dealing with geometric dimensions, it's dealing with forces. It's saying that the forces that act on a corresponding mass in the model and prototype are in the same ratio. So this is a key point, that the force on the model is going to equal the force on the prototype, and if we divide through by this, the force on the prototype is going to equal a constant. So it's forces that we're dealing with here. Dynamic similarity yields similarity of flow patterns, which is as long as the dimensional numbers work out, and we'll talk about that next. So if we look at a situation now where we have a spillway or some water spilling over a structure here down this incline, we can look at the forces on a particular fluid element. We've got gravity and these FV and FP forces here, pressure forces and velocity and acceleration and things like this. And so we the details of this are not as important as looking at the fact that we can build a model and have the same sort of forces. So if, in fact, we can scale completely between each of these individual forces and the resulting force is given right here on both of these. If we can scale these things down, as you can see, from large to small, we can, in fact, we can build a prototype like this and, in fact, use it in the lab setting to predict performance in the real world. So how do we go about doing this? I'm going to go ahead and just show you the derivation here. We're going to equate basically the gravitational forces for the prototype and the model, and we're going to be able to show that those reduce to the Froude number. And so this is basically we can see that the primary thing that drives this flow is the force of gravity here. So that is the relevant force that we need to think about. So let's get a new page here, and let's say that we're going to look at the force of gravity on the model over the force of gravity in the prototype, and that's just going to equal the mass of the model over the acceleration of the model over the mass of the prototype times the acceleration of the prototype. And so in the case that we were just looking at, the mass of the model or the mass of the prototype might be the mass of a fluid parcel excuse me, going over the structure. So we can write this down as we've seen before. This is just gamma times some characteristic volume so we're really just kind of doing dimensions here. We're just saying that the gammas in each different situation are listed here. Remember, this is rho g. So if we multiply by some kind of characteristic volume for each situation, we actually are getting mg out of this, mass times the force of gravity, or the acceleration of gravity. And so so that's the left-hand side. If we write down the right-hand side, we're going to have rho times Lm. This is just mg. I'm sorry, this is just a mass. This is just the mass, and the relevant, whoops, let me do that again. The relevant acceleration for this would be, in kind of dimensional terms again, would just be the velocity over the amount of time that we were looking at for the model. And of course, we're going to have a corresponding different set of parameters for the prototype. So the question is, how do these things scale, and what do we get out of the scaling? So if we reduce this, remembering that gamma equals rho times g, so we're going to get g in the equation. We note that, let me just do a little bit of canceling here. We note that these things cancel from both sides, and these things cancel from both sides, and we note that gamma equals rho g. So the densities are going to cancel, and all we're left with out of this is Vm, if we kind of write this on the other side, Gm times Tm is going to equal Vp, after some rearranging here, Gp over Tp. And noting that probably the accelerations of gravity are probably going to be equal. It's going to be pretty hard in the lab to change the acceleration of gravity, but so these things are probably equal. We also note that from before that Tm is equal to, can be written like this, Lm over V, and the ratio of Tm to Tp is going to be Lp over Vp. And we can use that, we can use this fact here to plug in for the times, and what we get out of this is we get that V squared, I'm sorry, Vm squared over Gm Lm is going to be equal to Vp squared over Gp Lp. And if we take the square root of both sides, we end up with Vm over the square root of Gm Lm equals Vp over the square root of Gp Lp. And these are just the Froude numbers for the model and the Froude numbers for the prototype. So now what we see is the power of similitude, in that we have for this particular situation right here, where we have a prototype structure that perhaps we've built or that we want to build, and a model which we can easily build in the laboratory. Those structures, we've showed that the Froude number is going to be equal for them. And if these g's are equal, then really we can, as soon as we scale down the model, the length scale of the model, and specify what sort, if we scale down the model, we're going to know what Lm is and Lp are, because this is going to be basically the length, say, of the height of this, perhaps might be the most relevant dimension. And if we know that ratio, what we want to have in our prototype ultimately when we actually build a thing, and what we want to scale it down into the lab, and then we know what velocity we want going over the structure, then that's going to tell us what the velocity in the lab needs to be in order to simulate the actual prototype situation. So that is the power of similitude. We can also, kind of switching gears here, we can also show for a different problem, by equating the viscous forces for the prototype and the model, we can show that the Reynolds numbers are also equal. And I'm not going to show this derivation, but but basically you can do a similar sort of thing and show that the Reynolds numbers are equal for the model and the prototype. This is frequently done. So in general, if the independent pi groups for the model and the prototype are equal, if you can show that, then the condition for dynamic similitude is satisfied, and you will be able to do um, things like this where you're able to build a model and simulate what's going to happen in the real world prototype situation. To have complete similitude, this is just kind of a definition, between a model and a prototype, it is necessary to actually have both geometric and dynamic similitude. Both the size of the model and the prototype, the ratios need to be consistent or constant, the ratio of the dimensions, and we need to be sure that the forces that we're interested in for that particular problem also scale, and that then we can use the pi groups to translate between the model and the prototype. So that's it. We have a whole series of ways of applying this. The conduits, valves, flow bodies, flow around buildings. The relevant thing for these sorts of problems is going to be the Reynolds number, because it's the kinetic forces versus the viscous forces that are going to be important. We'll work some examples next in class. Also, we'll look at 8.7, which is model prototype performance, do some scaling and look at the pi groups. And for this reason, measurements made by the model can be applied to the prototype. This is what we've been talking about. There's a whole series of examples of this. Then there's some special cases when we have high Reynolds numbers, when flow is high, when the velocities are high, typically. And we will talk about this, that at high Reynolds numbers, the viscous resistance is negligible. There's an example of that as we get back to this reverse flow nozzle thing. And then finally, spillway models in free surface models. We're going to be looking at can use the Fruit number here to solve some problems at the end of the chapter. Okay, that's it. And that's it for chapter 8. And in class, we will work several of these examples. Okay, thank you.